Hello. This is a really big room. Welcome to my talk. You might remember this under the working title of Smells Like Bare Metal from the conference program, but it's now been retitled From Blade Servers to Partitions. First, a few agenda points. I'll tell you a little bit about me, a few facts about Booking.com, set some expectations for the talk, and then I'll tell you about bare metal at Booking, the problem that we had with blade servers and their end of life, and our solution to that problem in the form of server partitions. And then I'll end with a few lessons learned, a shout out and a call to action, and some Q&A. About me. I'm a principal engineer at Booking.com. I'm based in Amsterdam. I have 30 years of industry experience. My specialties are virtualization, data storage, disaster recovery, and a few things about me. I live on a houseboat in Amsterdam. I love to travel, and I'm excited to be in Paris. A few facts about Booking.com. We're headquartered in Amsterdam, Netherlands. We have 29 plus million listings on our website with more than 174,000 destinations in over 220 countries and territories. Our website is supported in 45 different languages, and we have 100,000 plus servers, VMs, and containers. These operate primarily in 3 availability zones in Central and Western Europe. And a few expectations. There will be no case studies, product pitches, artificial intelligence, or misuse of on-premise. What you will get is a few old ideas, some history lessons, and some old school engineering. A bit about bare metal at Booking. We are a bare metal shop. We have been for many, many years. We are on a multi-stage journey to the cloud, but historically, we've just run on raw metal. And this has taken the form of majority blade servers, which have 16 cores, 32 threads, 128 gigabytes of RAM, a roughly 2 terabyte SSD, and a 10 gigabit network. I've been at Booking 10 years now. This was the standard 10 years ago when I joined, and it still is the standard today by which we run most of our infrastructure. These servers had a peak population of around 50,000, and they have a 2025 population of around 30,000 still. And they've been end of availability since 2020. And believe me, we were buying them right up until the very last quarter when they were being sold. So that makes these machines 5 to 10 years old in 2025. This is what large chunks of our data center look like. They're rows and rows and rows of nothing but blade servers. We get them from more than one manufacturer. If you squint really hard, you might be able to see the logos. But a shout out to our vendors. We love this stuff. You're great. We wish we could still get these things. This is a portion of one delivery from one quarter in 2018. And the same thing happened quarter over quarter over quarter for years on running. Which brings us to 2025, and we've got a few challenges. The first is data center efficiency. 10-year-old blade center technology is not the most efficient thing in the world compared to what modern chips can do. And we also have legacy applications. Tens of thousands of bare metal servers running your apps have a lot of inertia, and they're difficult to move. The end of the blade form factor is a big problem for us. We haven't really been able to replace it with anything equivalent. We're expected to modernize our platforms, more efficiency, being green, sustainability, more for less power. All of those things are big pressures. We have things like cloud native to deal with. We have containers to deal with, and virtual machines to contend with. And the timelines for all of this is not aligned. On one hand, we're under pressure to modernize our data centers, make them smaller, make them more efficient, and on the other hand, we're under pressure to move to newer architectures. And refactoring is slow. And this has delayed migrations, which has meant that legacy applications have been left behind. And we have the problem of blade server retirement. What do we do in this environment with all of these competing pressures? We have no replacement server SKU. We have no appetite for bringing new server models into the data center. And doing nothing is not possible. And we're under business pressure to modernize. So what do? We have limited engineering resources. And then there's the cloud. Everyone's talking about the cloud these days. So we took a look at what our teams were doing in the cloud, and we noticed something. Many teams use EC2 in AWS. Why? The acceptance level was actually quite high. Why? It's because they didn't have to refactor a whole lot. So we wondered, could we do something similar with our on-prem workloads that could not migrate to the cloud? Could an approach like EC2 work for these blade servers that we needed to replace? And if it could, what would we call it? We call it BC2. So what does BC2 stand for? It doesn't really stand for anything. It's quite obviously a pun on EC2, but if it were going to stand for something, it might stand for Booking EC2, Booking Compute 2, Bare Metal Compute 2, Blade Compute 2, or Blade Center 2. Any or all of the above. But what is it exactly? Sounds great. Could I have some, please? In a nutshell, BC2 is server partitioning of high-density server SKUs that were designed for modern cloud-native applications. It provides logical instances that equal or exceed the performance of legacy servers, or specifically legacy blade servers, of which we have tens of thousands. And it provides 100% compatibility with our legacy tooling, which means we don't have to require teams to refactor their workflows and provisioning. And this makes it virtually indistinguishable from blade servers for customers. In fact, we set out as a goal, we wanted to create a partitioning solution where customers could not tell the difference between what they were consuming now and the hardware that they used to consume. We have a certain technical philosophy when it comes to BC2 and bare metal engineering in general. That is boring and imperfect. And this comes from two places. The first is Dan McKinley, who has an excellent talk, if you look for it on Google, called Choose Boring Technology. And the basic premise that Dan has is choose technology that has known failure modes and few unknown unknowns. Everybody's chasing the new shiny thing, and new shiny things always come with a lot of things that you don't know about them. And sometimes when the problem that you're trying to solve is just move from point A to point B, it's easier and faster to just pick things that where you already know how they're going to break, because you figured out how to avoid how to break them in that way. And the next source of inspiration is Sir Robert Alexander Watson Watt. The picture in the sidebar is a radar station from Britain in the Second World War. And Sir Robert Alexander Watson Watt is the guy that invented the chain-home radar system. And when he did, he used what he had available rather than the best possible solution that he could build from a technical perspective. Specifically, he built radar that had a much lower frequency than what other countries were implementing. And he did this because the parts were readily available and could be purchased in large quantities. And when his colleagues asked him why he settled for such an imperfect solution, his response was, you have to go with the third best option when you're under time pressure. Because the second best option comes too late, and the best never comes at all. So what is server partitioning? What do I mean by that? Both EC2 and BC2 are examples of server partitioning. This is a very old idea that goes back all the way back to mainframes. In fact, the machine here on the sidebar is a Sun Enterprise 10,000 that I'm actually certified on. In 1997, if you were running a Solaris shop and you were one of the cool kids and had $1 million to spare, you could get one of these. It had a whopping 64 processors and 64 gigabytes of RAM, and it had a switchable backplane that you could carve up into 16 logical servers. And that's what BC2 is. It's a logical server carved out of a physical one. Resources are dedicated rather than being shared. And where hardware partitioning was the historical norm, as in the E10K and other machines of its era, software partitioning is the modern reality. We have big boxes, but we use software to turn it into logical ones. Now, this sounds a lot like virtualization, but it's different. Usually when you're talking about virtualization, you're talking about oversubscription in some form or another, and we do not do that. We provide direct hardware access everywhere possible, and we have a persistent rather than an ephemeral identity. Most virtualization frameworks create and destroy VMs on demand. They're not there until they're needed, and when they're not needed anymore, they're destroyed. But partitions have a long-lived identity, just like a physical server. It could belong to one customer one day, and another customer the next, and another customer the next after that, and it still retains a logical identity. It still is using the same pieces of hardware, and it still has the same logical identifiers that are used to track it through its life cycle. So, how does Amazon do EC2? If we were going to do our own version of this, what would we use? Well, we did a little research and found Amazon is now using KVM. They used to use Zen, but with the Nitro chipset, they switched to using their own version of KVM for many EC2 instance types that are available these days. This is a bit of an eye chart, simply because there are so many. But if you go to the Amazon webpage, you can find lots and lots of EC2 instances using the Nitro chipset. And this is only from a few days ago. I didn't even have room to show what they call bare metal instances, which are also based on the Nitro chipset. So there's a lot of KVM running around in Amazon, and customers using EC2 are using KVM without even knowing that they're using it. So we decided to use KVM for BC2. We do it a little bit differently, but we take the same basic building blocks that you'll find in a lot of other virtualization platforms. We take KVM plus QEMU and libvirt. This gives us fast kernel-based virtualization. It gives us a robust tool chain for creating and defining and manipulating virtual machines. And it gives us an API that has lots of language bindings that we can easily orchestrate with our native tooling. And then through BC2, we combine that with the other part of Booking's bare metal ecosystem, which consists of Foreman, our in-house provisioning system called ServerDB, and Puppet. The bottom part of this slide is how we have orchestrated bare metal for close to 2 decades now. And with BC2, we are now extending the same tool chain to virtual machines that in the form of partitions that are tightly mapped to hardware. So what does a BC2 host look like? Remember that I said that there was no appetite for new hardware SKUs. We didn't want to go shopping for more small servers. Blade servers are the size of a shoebox, and although you can find any number of multi-node chassis on the market today, we didn't want to go back to that style of buying things. So we went and talked to our cloud-native folks, specifically the ones that run Kubernetes, and said, hey, what are you using for Kubernetes clusters? And it turns out we had a perfectly good hardware SKU that we could adapt for our own purposes. And it looks like this. It starts with a 2U server chassis. It's split into 2 NUMA nodes. And in each NUMA node, there is a 48-core 96-thread processor and 768 gigabytes of RAM. This box has a total of 1.5 terabytes of RAM. That's 12 times more than our typical Blade server had with 128 gigs. To this server, okay, sorry about that. And to this server chassis, we add 2 15.36 terabyte NVMe drives. But if we need more, we actually have slots where we could go all the way up to 7, and these are hot pluggable, so they could be expanded on the fly. And the whole thing has 4 times 25 gigabit network in a 4-port LACP bond that is shared for the entire system. So what goes into a BC2 instance? Well, this is what the recipe looks like. If you're not familiar, this is Julia Child, a famous American chef known as the French chef. And if you want to cook your own version of BC2, what you need is 1 to 40 CPUs in pass-through mode. We'd like to use 1 gigabytes huge pages, but you can substitute 2 megabyte pages if you want. Take a pinch of I/O threads, not too much, you don't want to overseason. And use raw images for your virtual machines, but you should stir them really well until they're thick. You don't want your sauce to be too thin behind partitions. Every byte that the customer sees should be a byte that they are able to access. And very important, don't discard the trimmings. For those of you who don't get the joke, trim is an option that you can do on an SSD inside a VM. And if you're not careful, that will get passed through to the underlying host. And if too many of these things do these things concurrently, you can actually cause problems for the storage that's backing your VMs. So we disable this as an option completely in the virtualization layer, so that even if the customer is issuing trims or discard operations, they are completely ignored at the storage layer on the host. This works really well because we are using very, very large SSDs. And because the SSDs are so large, there's always a big chunk of unallocated, unused space, and the SSD will naturally use that space for housekeeping, which means you don't need to be as proactive about trimming and discarding blocks as you would if you had a small, much tighter on space SSD or even a consumer grade SSD. Those you do want to trim frequently, but if you have a very large enterprise capacity SSD, you can just defer this until the next time you re-provision your server. And then finally, garnish with serial number, MAC address, and IP. Serve hot and consume immediately. We've come up with a few different portion sizes. We've liberally copied Amazon's naming convention, but we chose to pick a letter of the alphabet that Amazon does not use, specifically the letter E. It doesn't mean anything in particular. It can mean whatever you want. Everything compute, extreme compute, excellent compute. It just doesn't collide with Amazon's instance families, which is why we used it. Right in the middle, we have the E1.large. This exactly matches our historical blade profile, with the one exception that it has fewer physical cores than that profile did. Booking workloads tend to be very low on CPU utilization. They care more about storage and memory. And we had half the number of physical cores relative to memory in these cloud-native boxes than we historically did in blades. So we just cut the number of physical cores in half. But other than that, it's basically a replacement for the blade. And then up and down the scale, we go to either half blade, quarter blade, or eighth blade, or then increase in size by doubling every time. As a multiple of the basic blade increment, 2x blade, 3x blade, 4x blade, and all the way up to a 5x blade. Now, one thing to note here is that we stop at a 5x blade with 640 gigabytes of RAM. This is because we cannot do anything larger in a single NUMA domain of the cloud-native chassis. So we deliberately confine the BC2 instance sizes to fit in one NUMA domain or the other, and we do not allow them to span across. This works just fine because the framing bar here actually shows the range of historical adoption that we think we'll be able to hit, and we've never had a blade server that was larger than the 4x large variant here. And we think that the most applications are going to stop right around here in terms of what they can actually consume. So within the constraints of a NUMA domain, we think we can replace all of our legacy blade use cases. So how does BC2 materialize in our environment? We need to connect these hardware-bound virtual machines into our bare metal ecosystem. And we start with a couple of basic identifiers. The first is we have a manufacturer ID, and then we have a model ID. And these are two very important keys in our provisioning system. And they are defined in libvirt and in the KVM definition through a couple of SMBIOS parameters called manufacturer and product. So by overriding the defaults of those settings, we actually create what our provisioning system sees as a new hardware model. It's as if we found a brand new manufacturer of blades and just rolled them into the data center and then started booting them up on the network. The network cannot tell any difference other than the fact that these have their own unique identifiers. We even went so far as to define our own unique MAC addressing scheme and serial number format that guarantees uniqueness across our environment and does not collide with any known hardware manufacturers. So how did we plug these unique instances into the provisioning system? Well, we created a fork in the road. The top level is a simplification of what we do with blade servers, which is we talk to a hardware-based API. It could be Redfish, it could be IPMI, it could be the server's native BNC, but we have to orchestrate it to do a number of different functions. The functions that we have, there's not that many of them. There's a PXE boot function, power off, power cycle, power on, power status, soft reseat, and power cycle BMC. That's it. That's all we need to orchestrate the provisioning of our bare metal servers. So what we did was we took Fast API, put it on top of libvirt, and created our own implementations of these functions to do the same things with the virtual machines as we do with the bare metal boxes. And then, of course, because it's a virtual machine, we don't need to power cycle the BMC. So we left that part out, but everything else is just completely abstracted. And up until this point, it executes the same code path as the bare metal provisioning infrastructure. So this is very important to keep in mind. It's exactly the same provisioning infrastructure that customers have used, exactly the same tool chain, right up until the point that the provisioning starts. So on top of this, there's a server discovery process. This is the part that connects Foreman, which some of you may be familiar with, to our ServerDB server management infrastructure. And once we create a new BC2 instance, we create a stub record in ServerDB. And then the first thing that has to be done is that machine has to boot onto the network and run the Foreman discovery image. So it will PXE boot, run Foreman discovery, and then discover facts about itself. These facts will then be uploaded to ServerDB, which will then add new facts to the original stub record and create a fully formed bare metal server record that is then ready for consumption. So this eye chart is the life cycle of a bare metal server. Apologies, I couldn't do it in a better resolution than this. But the life cycle of a BC2 instance is exactly the same, except it spends all of its time in a subset of this chart. So there's lots of stuff related to bare metal, such as delivery, racking, install, lots of stuff that a virtual machine does not have to go through. So if you look at the life cycle of a BC2 instance, we start in racked status. This is another difference between BC2 and a typical virtualization platform. Because we're using a bare metal workflow, we actually have to have the virtual machines exist in advance of use. So this means we have to go to customers and get them to tell us, how many machines do you need next week or next quarter or through the rest of this year, and we make sure that those sizes are provisioned for them in advance. This is exactly like server orders used to work. Customers would tell us they need X number of a certain size of blade server, and we would make sure those got ordered and delivered and installed and were made provisionable when they needed them. There's then a life cycle that goes through reserved, hardware setup, needs operating system, needs setup, installed, and finally live, which is when the application actually is ready to serve traffic. And then from live status, when a workload gets decommissioned, there's a deprovisioning workflow, the server gets probed and tested again, and finally goes back to racked status for the next customer. What's really unique about BC2 compared to the bare metal is how fast these processes go. These are processes that on bare metal servers would take dozens of minutes or even longer, depending on how the hardware was feeling on any given day. But now the process from provisioning from a racked spare machine all the way up to the application is live is 10 minutes. And even more impressive is when you're done with that server and you go and put it back in the pool, the deprovisioning process to racked status takes 10 seconds. We just blow away the disk, recreate it, reset all of the statuses, and the machine is ready to go for the next customer. There's a final status that gets used if we actually delete a virtual machine so that it logically no longer exists on a hypervisor. We also use a status called blocked, which is normally used to represent a server that is unavailable for one reason or the other, but is expected to come back into productive use at some point. So it doesn't lose its identity, it doesn't lose its MAC address or IP. It's there ready to be logically recreated. Except with BC2, it could come back as a different size than it was previously, which is logically kind of the same thing as having a data center engineer go and plug more RAM chips or more SSDs into a physical box, and then you reboot the thing with the same serial number again. Reprovisioning a BC2 instance as a different size with more cores, more memory, or more storage is effectively the same thing. The core identifiers stay the same, just the resources attached to it are different before it's brought back in and made available to customers again. This is what our virtual BMC looks like. It's very similar to a hardware BMC. This is intentional, but what's not immediately visible here is the integration with our single sign-on processes. So our workloads are defined in, in Puppet through a system that we call server roles, and server roles have people with access to them based on team identity or special privileges. And our virtual BMC can detect the user, and if they're trying to access the BMC of a BC2 instance, and they are one of the people authorized to access that server role, they are then also granted access to the virtual BMC, and the whole process just takes a couple of clicks. So customers running a bare metal workload on top of a virtual instance also get access to see the physical console, so that when something has gone horribly wrong, they can see what messages are appearing on the screen. This is what the console looks like. It's nothing special. It looks just like any other hardware BMC, and it's supposed to. So we learned a few things along the way that I'll just try to summarize as quickly as I can. The first is VMs can outperform bare metal, or rather, a VM on a modern piece of hardware can easily outperform 5 to 10-year-old bare metal, which is the frame of reference our customers had. So the bar was set pretty low. But nonetheless, the feedback we've had from our early testers is they either cannot tell the difference, or it's noticeably faster. Hiding NUMA from customers has also been a great benefit, because the VMs are either in one NUMA domain or the other. So from a customer perspective, all they get is a single socket server, a single memory address space, and they don't even have to worry about tuning their applications. All of those blade servers that we're replacing are 2-socket machines. So there's a lot of legacy code out there that is desperately trying to optimize for NUMA, and now they don't have to worry about it. We also learned that legacy abstractions can be very, very sticky. So aiming for 100% compatibility with older APIs, even if it's not as forward-looking as we would like to be, has great benefits in terms of migration speed. And simple architecture helps you meet deadlines. The customers we've talked to, when they're given a deadline, this is just as if we handed them another fleet of bare metal servers and said, go move your workload from point A to point B. They don't have to worry about refactoring for another provisioning interface, another set of tooling. It's just another piece of infrastructure for them to consume. We also learned it's possible to be too fast. We ran into a number of cases where the VMs were just booting too fast and going live too fast to actually they actually broke some parts of our processes. There was a DHCP race condition that forced us to do IP address allocation in advance when we created virtual machine records, because the bonded NICs just were competing with each other. We also had an issue with our Vault credentials. There's a database that makes Vault that knows about servers as they're provisioned, and it takes about 7 minutes for that database to be in sync from the moment that the provisioning starts to the moment that the server tries to consume the credentials. And the VM was ready to consume the credentials at about minute 4. So we've had to address that. Some customers have told us that the network is inexplicably faster. You know, a customer doing nothing other than I/O pings to an NFS share asked, "Why is this 20 microseconds faster than on the old thing?" So that's what we've learned. I was asked to put together a call to action. We're in Paris, so this is a reference to the Paris Commune. I'm going to repeat a few things that have been said already. We'd like to encourage our software and hardware vendors to participate as much as possible in the open source ecosystem. Open firmware management is something we would dearly love to see. Firmware issues are very high on the list of things that we've had to deal with. NVMe vendors, please support SRIOV. One of the things we would like to be able to do with BC2 is provide hardware access to NVMe devices, but we don't have enough NVMe devices to go around. So we want to be able to carve up the NVMEs into smaller instances and just use PCI pass-through to the VMs. So please support SRIOV. The SSDs are getting bigger, and we can't consume them all from a single instance. And that said, dear OEMs, please stop disabling SRIOV in the firmware when it already supports it. You know who you are.
We know.
We would like to see more future-proofing of parts and interchangeability. This ties into NVMe SSDs in general. We've had lots of issues with incompatible backplanes, incompatible drive carriers, things that don't have to change as much as they've been changing from one generation to the next, but mysteriously are. And this has actually resulted in us having a mismatch of very nice, very expensive NVMe SSDs that we could not move from one generation of hardware to the next, even though those hardware generations were just a single generation removed from each other. And technically, the hardware should have been compatible, but these other things wrapped around it ensured that it wasn't. So please have an eye towards future-proofing and compatibility, because the stuff like NVMe SSDs potentially has a much longer service life than the hardware we're wrapping around it. And it's nice to be able to reuse those components. We would like to see toolless, screwless drive caddies. This is one of my personal bugbears going back many, many years. I still see lots of drive caddies that, despite an SSD having no moving parts, have 4 tiny little screws that are attaching the SSD. That toolkit that was provided to everyone is going to come in very handy for doing SSD swaps. A big shout out to one of our vendors, who I will not name. At least they only have 2 screws in their caddy now instead of 4. So you're going in the right direction. We would like to see more of a focus on single socket servers, but with really big fans. We still see a lot of one-use servers which are really difficult to air cool at certain densities, because the fans take a lot of power and require a lot of RPMs. So instead of putting everything in a 1U chassis and spreading it across the entire rack, maybe think about bumping that up to a 2U form factor. Use the big fans that you can get in a 2U box, but just to put 2 servers side by side so you can get better airflow and more efficiency. And here's the image credits if you want to see what any of the public domain or other images came from. And thank you very much.
Me again. Hello. You said that the user experience was as seamless as possible. Mm-hmm. Did you go down the rabbit hole that deep that you filter out CPU instructions for older applications? Because, for instance, you have SIMD instructions that are usable now that weren't earlier. So you might have different behavior for the code. Do you go this far yet? or do you intend to?
We have not had to go that far yet, but we'll see what our customers tell us. We don't think there's any workloads out there that are bound to specific instructions, like AVX or something similar to that, but we might have to do that if we run into certain cases.
Hi, great talk. Can you describe firmware shepherd?
Firmware shepherd.
It was on your slides, the workflow slides where the firmware was updated and went round.
I'll have to get one of our other guys to talk about that.
It seems like it's quite onerous when it comes to Lifecycle.
Yeah, we do have this thing called firmware shepherd that our update firmware process is complicated.
Well, I saw the whites of your eyes when I mentioned it.
Yeah. We don't have anything resembling a unified approach to firmware, if that's what you're asking. But yes, we have made various attempts over the years to unify that process, so far unsuccessfully.
Thank you.
Thank you for the presentation. I cried a little when I saw that you disabled discard on your SSDs, and I realized you might not have a choice. There might be kernel patches that you can look at that could help in your case, but there's also the fact that maybe you're also working around firmware bugs. We're back to firmware bugs inside the SSDs. If you discard and it's affecting other IOs, yeah. So we're back to what we were talking about.
Yes, we actually don't discard, we don't disable discards completely, but our natural workload lifecycle means that everything, including the hypervisor, will get re-provisioned about once every 6 months. So twice a year, the hypervisor itself will get re-provisioned, and in the process of reformatting the storage, the file system will issue a discard over the entire drive. So it just means we go from doing discards hourly or weekly to once every 6 months.
Hi. How about the network? I mean, it has each VM its own IP address. Can it move from one host to the other? And how do you move the data on the disks?
So we've gone with entirely local ephemeral storage that is tied to the VMs. At the moment, we are tying VMs to the hypervisors that they are in. So there's no concept or intention to move VMs from one node to the next. Therefore, we don't need to preserve the data. If we need to evacuate a hypervisor, we have a maintenance API, and these are distributed redundant workloads, so customers are very familiar with this from a blade server perspective. They just use the same workflow that they would use to evacuate a blade server in one rack and provision the workload in another rack, and the same process works with the VM. That said, from a technical perspective, moving VMs is possible. Every rack has its own broadcast domain, so potentially you could move VMs vertically within a single rack for maintenance purposes. We are exploring that. We're not sure if we'll do it, but it is possible we could do that for break-fix workflows or for patching hypervisors.
And everybody is on the same level 2 network, or how?
All nodes in the same rack are in the same layer 2 network, and the VMs are bridged into the same network as the hypervisor itself. Something I was not explicit about, but these hypervisors, they coexist in bare metal racks with other compute workloads. So the same exact provisioning workflow that provisions a Kubernetes server will be used to provision a BC2 host. And then on the BC2 host, you have the partitions that are booted into the same network, and they draw their IP addresses from the same pool.